Once upon a time, there was this startup cube. At that pretty moment, it couldn't even think that the cunning creator was just in the beginning of the cloth simulation tutorial. What have you done, oh mighty creator? Am I supposed to be like this till the rest of the modeling? Don't worry, startup cube, I'm gonna make it better. But where shall I start? Well, you can always check the manual. It's got almost every important thing to know. Let's start with giving more vertices to our mesh. Make sure your mesh is equally subdivided unless you want something specific. Add the cloth modifier. Select a cloth preset. Add a collision object. Adjust its shape and position. Assign collision modifier. Hit play and watch your simulation flowing. After, you can add a subdivision modifier to enhance its look, for instance. Also remember, cloth simulation depends on the modifiers before, not following after. It's better to bake the whole simulation beforehand. What if I jump to the last frame instead, Your simulation will not be calculated up to this frame. If you bake your simulations, you can switch between different objects and have a quick access to the simulations at any time. However, it can cost you your computer resources. Make sure your cloth mesh doesn't penetrate any of the collision objects or too close to the surface. Alright, I get it. Now I can simulate the tiniest cloth in the Blender world. What is this? What's happening? The thing is, the mighty creator, that all of your meshes here are too small to have your simulation work precisely. If you have a human model, raise its scale about 20 times higher. Later on, you can apply everything and scale it back. First of all, you can start with choosing a cloth preset. Each gives different physical qualities to your cloth. They are defined by physical properties, stiffness, and damping. Quality steps increase cloth simulation's accuracy. This can slow down your simulation process, but it helps a lot if your mesh penetrates or stacks in collision objects. Speed multiplier can slow down or accelerate the simulation's progression. It could be helpful for slow motion simulations or examining your simulation in detail, for example. Vertex mass stands for mass of each vertex. The number of vertices not only influences the quality and amount of wrinkles, but it also makes the mesh heavier. It increases the weight of the cloth and affects its physical qualities. Two meshes with the same vertex mass, but different number of vertices, will have different weights. Vertex mass makes difference when the cloth interacts with the collision object. It doesn't affect the speed of falling due to physical laws. Air viscosity determines the air resistance. The higher is the value, the smoother the cloth moves or falls in the environment, the less wrinkles you can expect. Angular bending model is the newest model that splits structural into tension and compression attributes. Structural belongs to the old linear bending model. In short, angular model makes simulation more realistic. Check the difference on this page. The combination of stiffness and damping attributes influence the character of the cloth and can be defined by the cloth presets. They all affect the resistance of the material. Tension controls stretching. Low tension allows the material to behave like silk and envelope objects. High tension keeps the material shape within the original boundaries, producing less wrinkles. It makes the cloth resist expanding in whatever outer direction. Compression prevents the material from shrinking. The red bars show how the sides are narrowed on the low or high compression value. There is much more deformation happening on the right. When compression's value is low, we can see its size squeezing. There is much less deformation in the left example, because the compression resistance is high. Shear implements the cross or diagonal resistance. If shear's value is high, the diagonal fluctuation becomes low and sharp, as if it cuts the surface across, especially when tension and compression resistances are much lower. If shear's value is low, the cross fluctuation becomes smooth. If we raise these attributes, our mesh will be more resistant to deformation. With lower values, our material becomes loose, more relaxed. Bending is a coefficient which amplifies the size of the wrinkles. With a high value, we get larger folds. It can also inflate the aerial shape at specific settings when tension, compression, and shear are low enough. Damping affects all these parameters. It suppresses fluctuations inside the wrinkles. With zero damping, we have most of the wrinkles. As its value grows, we see less distinguishing folds on the surface. However, if it overcomes a certain value, we get artifacts all over the place. In general, with a high damping, we get a smoother surface. Should you change the mass or number of vertices, for instance, you have to tweak stiffness and damping if you want to keep the material's character. Internal springs act as three-dimensional springs and work for meshes with a volume. It means if you check internal springs for a drape, for example, you won't see difference. However, if you apply it for a volume mesh, you will notice it. Internal springs make the mesh behave like a solid or soft body. The mesh basically retracts the deformation to its original condition. Max spring creation length is set to 0 by default, meaning that the length of the springs has no limits. If we give it some low value, the mesh will deform softer. Max creation diversion determines the angle which the internal springs can retract to. The less is the angle of the strength, the less the internal springs have power over the mesh. To see the difference, you have to set the length to something like the value of 2. The whole cloth simulation highly relies on face normals orientation. Check surface normals actually considers face normals orientation. If we recalculate the normals of the top surface and sides, for example, it will sag during the simulation because the internal springs will not affect it. If we uncheck it, the simulation will behave like all the normals have the right directions, but still it will make some inaccurate calculations. All your face normals should be calculated outside in order to have correct cloth simulation and everything else in your workflow. Tension and compression make the stiffness of the internal springs. The lower is the stiffness, the more the mesh gets deformed. The higher is tension, the more the mesh resists stretching. The higher is compression, the more the mesh resists shrinking. Vertex group specifies which part of the mesh will have the maximum stiffness of the internal springs. Max tension and compression will be applied locally by the vertex group. Pressure makes the mesh behave as if it's filled with fluid like gas or liquid. You can then increase the positive or inflating pressure or set a negative value to make the mesh squeeze. With custom volume, we can set the initial volume of the mesh by tweaking the target volume. If we change the pressure dynamically, then return it to 0, the mesh will deform back to its original volume. If we don't customize the target volume, it will be 0 by default. Factor is the coefficient for the aerial pressure comprised of pressure and target volume. When factor is 0, neither pressure nor target volume is applied. Vertex group defines parts of the mesh to which pressure settings will be applied. With this option, you can make a mesh move like a balloon, for example. You can adjust the vertex group with weight paint. The dark blue or zero weight areas are not influenced by pressure or make the target volume, while the red areas have the maximum value. You have to switch to object mode again to have everything work correctly. Notice how it's changed the influence on the cube. Make sure your mesh has a clean, undamaged topology. A non-manifold mesh is generally defined by bad topology with holes and faces inside, for example. You can still use pressure attribute for non-manifold meshes. However, you can get inaccurate simulation. By utilizing cache property, you can bake your simulation and watch it place without delays. It's a great attribute to test your simulation and check it in detail. Notice that adding subdivision modifier after might slow down your animation. Cache is especially helpful when you have different cloth meshes. You can check the quality of all simulations by switching between frames without having to play the simulation from the beginning. Notice that keeping the baked data can also consume memory resources. You can make and store different simulations in the cache list. Always give a name for a new cache slot, otherwise all the unnamed cache slots will actually bear the name of the mesh. When you create a different physics simulation and want to use a cache, give it a name. Make sure you've set up the range before you click Bake, otherwise you'll have to wait until it's done. Blender stores baked simulations in the blend file by default. If you check Disk Cache and bake it, it will create a folder alongside the blend file and store the cache file separately. You have to save your blend file first to use this option. When your library path is enabled, the linked physics objects in different blend files will reference the same disk cache, otherwise they will use independent caches. So these two options come along together. You can compress the disk cache files to reduce their size, especially for complex simulations. Heavy option can take time, but the compressed files will be way lighter than before. Calculate to frame bakes the simulation up to the current frame into the temporary cache. Now you can watch your simulation. Click on the cache in the list to make this option available again. Now, if you move back in animation, you will delete frames from the cache memory. If you play the animation, Blender will create a temporarily cached simulation. To save this simulation, you can press Current Cache to bake. Bake All Dynamics bakes all the physics simulations in this scene. It means you can bake a simulation for every mesh into its current cache at once. Utilizing Bake All Dynamics is faster than baking a simulation for every mesh individually. Deletes all bakes transforms all the cache simulations in the scene into temporary. You can simply clean it if you switch to frame 0 and click on the cache. Updates Auto Frame bakes all the physics simulations in the scene up to the current frame and stores it as temporarily cached simulation data. If you decide to move your cloth object with a baked simulation, you'll have to rebake it or add another cache slot. In this example, I delete and bake again. Now you can have a new animation. If you want to copy the object and preserve its cache settings, copy it with Ctrl-C and paste it with Ctrl-V, but change all the cache names if they are the same. This is necessary to avoid simulation errors, especially if you use disk cache. You can copy with Shift-D, but it resets the cache list. Notice that subdivision levels must be equal for preview and render if you want to render the animation straight ahead. You can pin your mesh by selecting a group of vertices with a maximum weight value. Go to Object Data Properties tab. Create a new vertex group and assign vertices for it. Go to Physics Properties. Select this group as Pin Group. Now the cloth will hang on these pinned vertices. It will make sense to adjust stiffness if you define a vertex group by weight painting. The strength of the colored areas can be increased or decreased depending on the stiffness value. You can get different results by changing its value. Paint vertices are often used for shape keys animations. Sewing makes edge-connected vertices pull to each other. This method is applied to create clothing or bind different cloth parts for any other reason. Make sure that face normals are calculated outside the mesh. Select the opposite vertices. Connect the opposite vertices with bridge loft. Select faces and delete only faces. The number of faces here is a bit high for a quick test, but it's okay if you want to get more wrinkles. Bake the simulation to work with it faster. Now we can observe the simulation without delays because it's contained in the cache. Apply all the modifiers, including cloth modifier. However, I will need subdivision modifier to see a smoother surface later. Select all the vertices, press F3, fill holes. I'd like to avoid pinching at the areas where the edge loops are too close. So I'm going to merge them together, but leave a quartz in the middle to have two 5-edge pulls here instead of one 6-edge pull. I'm merging the overlapping vertices by distance. Now I'm going to have a chord between the pulls. Do the same for the other side. Uncheck the shading with the subdivision modifier and by setting smooth to the whole mesh. I'm looking for glitches and undesirable pinching. If it looks fine to you, consider checking face normals orientation. Finally, if everything is okay, do the retopology and bake a normal map as an option, or proceed with another cloth simulation. To make best of sewing, you have to adjust other parameters, at least such as quality steps, collision distance, and perhaps gravity. Max sewing force defines how strong the vertices are pulled together. It has unlimited force at 0 value. You can set it to something like 10 and watch the sewing strings being pulled slower, but making the simulation more accurate. In this example, you can also add some pinpoints at the sides to pull the t-shirt down a bit. Notice I have set gravity to 0 to prevent the t-shirt from falling due to low sewing force. You can shrink or inflate cloth with shrinking factor. When it's positive, the whole mesh shrinks and attaches to the collision mesh tighter. You can achieve the opposite effect with a negative value. This way a t-shirt might look more spacious, for example. Dynamic mesh property allows you to deform the mesh with the shape keys or deform modifiers and make the simulation recalculate the shape each frame the deformation appears. All the modifiers must be above the cloth modifier. However, it is still possible to animate with the shape keys, but without dynamic mesh property. You just have to animate paint vertices. Collision defines how precisely the cloth mesh interacts with collision objects. Quality provides more accurate computations, avoiding penetrations and other simulation inaccuracies. Distance defines collision distance between the cloth and collision object. You can put it down to the lowest value to reach more realistic results. However, you might get some simulation errors if quality isn't high enough. Larger values can be less realistic and provide slower computation. Overall, it especially makes sense to put its value down for smaller objects. If your cloth closer than distance or intersects the collision object, it may experience an explosion. Impulse clamping restricts motion in complicated collisions to avoid explosions. This attribute has impact if it's above 0. If you add collision collection, your mesh will interact only with collision meshes placed in the selected collection. This plane has the collision modifier, however the cloth mesh will ignore it. Self-collision prevents cloth from intersecting itself. It is mainly useful when it creates cloth meshes with many wrinkles. It is also pretty much resource consuming. Friction is a coefficient of surface resistance to rubbing against itself or different surface. The cube and the drape actually comprise a whole cloth simulation mesh, where the cube belongs to the pin vertex group. When the cloth collides with itself, friction restricts motion at the collision areas. Friction should be determined according to the type of the material. Distance defines collision distance between parts of the cloth. Keep distance low if you want more realistic results for smaller meshes. Usually, the value in the middle is fine for big objects. Impulse clamping prevents explosions in self-collisions. It makes sense to adjust impulse clamping if your meshes are small and there is not enough distance between the cloth and collision objects. Anyway, it's better to enlarge your meshes to improve accuracy in physics simulations. Also, remember to apply all transforms. You can define a vertex group for the parts that you want to collide with each other. The red surface is the vertex group. The white part of the cloth ignores the red part. You can use property weights to adjust general attributes locally with vertex groups. Structural group controls structural stiffness locally, made by tension and compression. Shear group defines an area with maximum shear stiffness. Bending group defines a vertex group to control bending stiffness locally as well. Shrinking group defines parts of the mesh which will be shrinking. Cloth can be influenced by different forces with field weights. You can animate gravity by changing its values from positive to negative and vice versa, for example. You can add external force fields and combine them with existing values. The closer is the force field, the more impact it has on the mesh. You can also group forces for the effector collection. Only the force fields in this collection will have an effect on the mesh. Such parameters as vertex mass, stiffness, damping, internal springs, and pressure make the character of the cloth. Define quality steps and collisions to improve the quality of the simulation. Squish and squash characters' clothes with dynamic mesh. Sew your cloth patterns with sewing attributes. Make your simulation more dynamic with different forces. You can set negative values for pressure, shrinking factor, and fill weights. You can animate every attribute marked yellow. Combine attributes to achieve best results. Great! I've made a perfect simulation. Now let's just apply these... What? Something's not right. Well, it's not that bad. As an option, you can export your model as OBJ or FBX and import it back. Alright, Startup Cube, I'm ready to rescue right away. Let's just put the strength to 0. Oh, looks better than before. Okay, what if this time we try some... what?